Okay, we are continuing on here with chapter 7. So last time we started talking about types of reactions. And remember, last time we talked about there's really sort of two big classifications of reactions that sort of a more specific way you could classify the same reaction sort of fall under. So the one we started talking about last time is really the double displacement reactions, kind of like the experiment we did. And with a double displacement reactions, as I mentioned, it's sort of the big umbrella classification of the type of reaction that's taking place. Underneath them, as we talked about last time and we'll talk about today, we have things like precipitation reactions, which are obviously reactions that make it solid. We also have acid-base reactions, as we'll talk about next here, which basically will form water. So there are more specific ways to classify double displacement reactions, but it is sort of the big umbrella, which, you can just simply classify a reaction as a double displacement reaction. But again, sometimes people want to kind of more specifically classify those. The way that we recognize really double displacement reactions is pretty simple. They are really the only type of reactions that you'll come across where you basically have two ionic compounds coming together. So you got two guys that have a positive and negative ions that have come together to make ionic compounds. So you could always recognize these type of reactions as you got one guy that's a positive negative together, another guy that's an ionic compound that's really a positive ion and a negative ion together. And 100% of the time, the way these reactions always take place is it's really the positive guys that end up basically just switching partners. So in this particular example here, A would end up with D. Remember, obviously, the two positive guys can't come together or the two negative guys can't come together. So really your only option is the guy in one goes finds the negative guy in the other, and the negative guy goes finds the positive guy in the other case as well. So C here would then go and sort of find B. The result of that is, again, we will make two new ionic compounds on our product side of the reaction. And this is, again, always the way that these double displacement reactions take place. Now, we did talk about last time, and it's really important, and where people, again, really screw up a lot is they got the reactant side of this type of reaction, and they need to kind of predict the products on the other side and then balance the equation. And as we talked about, what you want to do is really first make sure that you get the correct ionic compounds on the right-hand side of the arrow. So you want to put them together like we were doing with nomenclature and all that kind of stuff, just balance out the charge. And then you want to go back and change the coefficients to balance it. Again, you don't want to, when you get to this side, try to balance and create the formula at the same time. As we talked about, you will end up with probably the wrong formula and nothing will balance. Now, the result of this reaction really will pretty much result in one of two things being formed on the product side here. As we talked about last time, we will sometimes have a precipitate that's formed, sometimes abbreviated PPT. And that's why these type of reactions are sometimes called precipitation reactions, because the result of basically mixing two ionic compounds together will sometimes result in a solid being formed. Remember that pretty much when you have ionic compounds together, when they are in really a solution, they're not together. They're typically strong electrolytes, which means you essentially got positive and negative guys basically floating around in that solution. We looked at solubility rules, which helped us understand that if we get sort of a certain combination of positive and negative guys that come together, they may form a solid, and in other cases, they may not form a solid. And that's how we can sort of predict when we mix two things together, should we expect a solid to form by using those solubility rules that we talked about, I think, last time as well, to help us do that. So again, in certain cases, there will be a strong attraction between these two ions, which then will essentially kind of precipitate those guys out of solution as a solid in this particular reaction. And the other result is what we're going to kind of talk about here today is when you mix these two things, especially in a sort of acid-base situation, we will get some type of water basically will be formed. And water is typically formed in this result when we got acid and bases, because there's really two ions involved. There's H plus and OH minus, which has a very strong attraction to one another to want to form water. And we also talked about really there's sort of three driving forces as to why sort of chemical reactions really do take place. And these are really two of the three reasons why a reaction takes place. The three reasons really driving forces for chemical reactions is a precipitate is formed in a precipitation reaction, the formation of water, like what we see in an acid-base reaction. And what we'll talk about at the end of this chapter here is really electrons being transferred, which occurs in redox reactions. So those are really the three reasons why, you know, we say, oh, this chemical reaction sort of take place, is basically one of those three things is sort of happening in this process. And again, with double displacement reactions, it's pretty much the solid being formed or water being formed as the kind of two main things that are happening. Any questions on any of that stuff there? Okay, so I think we did a lot on that double displacement reactions with precipitation reactions. In addition, we also talked about three ways we could kind of display those reactions: the molecular equation, the total ionic equation, and also the net ionic equation, where we have spectator ions that are going around. Remember that the net ionic equation really, in pretty much all cases, sort of gets rid of everything else and basically tells you exactly what's taking place, you know, when you do that reaction. So I think we finished up maybe on one like this. And again, this guy at the bottom, I think we finished last time. That's our net ionic equation after we got rid of our spectator ions. Spectator ions, again, are ions that are really there just to balance out charges, but they really are not leading to any sort of product formation, no solid being formed, no water, anything like that. And what's really happening in this case, where we mix really silver nitrate with sodium chloride, is the silver ion from the silver nitrate is going to go find the chloride ion from the sodium chloride, and those two together, based on solubility rules, have a very high attraction to each other, and they're going to basically come together and precipitate out of solution, and you would see obviously a white solid that was formed as a result of that. Any questions on any of that there? Okay, so kind of continuing under the umbrella of double displacement reactions, are acid-base reactions. There are sometimes, as we will see, called acid-base neutralization reactions. And as we will see, the main reason for that is we are forming water as a result of this. So just a reminder, a couple of things that I think we might have talked about when we're doing some naming and stuff like that, but acids, they typically have sour taste. They cause litmus paper to change color, which I think you used a little bit of litmus paper the other day. Typically, if you have blue litmus paper and you put something on it and it turns red, or technically speaking, any litmus paper that technically turns red or stays red, that usually means it's some type of acid or acidic type solution that you're dealing with. They react with certain metals to produce hydrogen gas. So I think maybe one of the reactions we did the other week or last week was you took some magnesium turnings, I think, and you put some hydrochloric acid in it, and you saw bubbles occur. I think we did the barking of the splint, I think, as well. And that, again, is those bubbles that you're seeing is the hydrogen gas being liberated as a result of a single replacement reaction, which we'll talk about here in just a bit. And obviously, bases, on the other hand, they have bitter taste. They feel slippery. A lot of soaps or bases. They also turn litmus paper typically blue. So if you're using any type of litmus paper and either it stays blue or turns blue, it is a basic type of situation that's sort of occurring in that deal. A lot of strong bases, as we probably talked about as well, do come from group 1 and group 2 on the periodic table, and they typically have hydroxide in them. So things like potassium hydroxide, sodium hydroxide, those guys are usually pretty strong bases. The sort of definition of an acid, again, is the ability to produce H+ or protons in solution. And sometimes H+ is called a proton, especially when you're dealing with acid-base chemistry. Again, because hydrogen has a proton, an electron, and no neutrons. So in order for it to become positively charged, it has to lose its electron, which leaves it just a proton. So when people talk about protons, they're talking about H+s. And also H3O+, which is the hydronium ion, is also interchanged a lot in acid-base chemistry with each other. But that's basically your definition of something that's an acid, is basically when it's in a solution, it has that ability to produce a lot of times, of H+s that are free in that solution, basically floating around. There are some strong acids, which are strong electrolytes, and we talked about electrolytes the other day as well. So a reminder that electrolytes are things that when they go for a swim in solution, basically break apart and produce ions. The production of those ions is what helps sort of complete all the circuits, if you will, and conduct electricity really well. There's strong electrolytes, which 100% break apart in solution. There's none of those units still together. And strong acids are strong electrolytes. So these are some examples of some strong acids. Some other ones are hydrobromic acid, hydroiodic acid, perchloric acid. So these are some examples of strong acids. And again, in solution, like it shows here, 100% of what you would have happening there if you had nitric acid in solution is it would break apart into H+ ions and nitrate ions floating around. And 100% in solution is what you have here. You pretty much have none of this guy still together in solution. And that's really why it's considered a strong acid, because pretty much all it needs to do is go for a swim. It will produce a lot of free H+, and thus it is a very strong acid. There's obviously weak acids, which are also weak electrolytes. And much like we talked about with weak electrolytes, they will basically stay together, but will produce a little bit of H+. So they're still considered acids, but they're not as strong acids. Any questions on that there? Now, bases, same deal. As I mentioned before, bases actually kind of do the opposite thing. Bases are things that have the ability in solution to produce hydroxide ions. So the ability to produce free OH- solutions floating around in that solution is really what makes something a base. And strong bases, as I just mentioned a second ago, pretty much have hydroxide in it. Again, if you kind of go on the periodic table there where like lithium is, and then there's like sodium, then there's potassium, then you hang over to calcium and come down to like strontium and barium. Any of those guys there with OH in the formula, probably going to be a strong base. And again, group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic. So that's, why they're sort of called those guys. And again, a lot of our strong bases actually do come from that. Not all bases have hydroxide in it. So there are some weak bases that do not actually contain hydroxide, but they're able to produce hydroxide. So, something like ammonia, for example, that is actually a base, but it is a weak base. And when it is in water, what it's able to do basically is grab an H+ off of water. And the result of that is it will make NH4+, and it will be able to produce some hydroxide. But in this case, as you can see, it's got to go find some water. It's got to do a little reaction to kind of produce hydroxide. And that's very different than if you just took something like sodium hydroxide into solution. It's just going to break apart right away and produce a lot of hydroxide very, very quickly. And again, this is sort of a weak electrolyte situation, which means you'll have a lot more of this guy in solution, but you still will have some of the hydroxide. And again, that's why it's considered more of a weak base than a strong base. But again, sometimes people are like, how could that be a base? It doesn't have OH in it, but it's able to really produce hydroxide or OH-. And that's really your definition of what really a base is something that's able to kind of produce it. And again, strong bases or strong electrolytes, they are basically carrying their hydroxide with them. So when they go for a swim, it's produced right away. Again, weak bases got to kind of go and do a little reaction to produce that hydroxide. Any questions on that? So the reaction of a strong base and a strong acid will pretty much always end up in the same result, no matter what combination of strong acid or strong base that you put together. You basically always end up with the formation of water. So typically speaking, when we react an acid with a base, we typically get what are referred to as basically two things that are formed in this reaction, and that is a salt and water is basically what is sort of always formed in this reaction. A salt is just an ionic compound. So that's basically what a salt is. It's just an ionic compound, and water obviously is H2O. Where does really the water come from? It comes from the acid, which basically contributes the H+, and the base, basically contributes the OH minus, and it's that H plus and OH minus that come together basically to form water. That is important, as we talked about earlier, as one of the major driving forces for chemical reaction is the formation of water. So that's basically what is happening in these reactions. Obviously, very different than other ones is you can't visually see it unless you do something, but you can't really visually see, oh, I just made water. So unlike a precipitation reaction, where you can actually see the solid being made, obviously, sometimes you mix it together and it looks like, well, nothing much happened. But again, you can't really necessarily see that formation of water, but it is sort of occurring. These type of reactions are also double displacement reactions. So if we took something like hydrochloric acid plus our sodium hydroxide, this is also just a classic double displacement reaction. That's a positive negative guy. That's a positive and negative guy. So that setup right there should basically show you that it's a double displacement reaction happening. And even if you can't remember that you should make salt and water, you just do the switch of the ions. That means in this case, the H plus and the OH minus to come together. And again, when that H plus and OH minus comes together, that is where that water is going to be formed. The other result is the sodium ion and the chloride ion coming together, sodium being positive 1, chloride being negative 1, which gives us some sodium chloride that's going to be made here. And that is our salt in this case. Yeah. So that is our salt, the sodium chloride. And obviously H2O is our water. So these acid-base reactions or acid-base neutralization reactions, they are ultimately really double displacement reactions. They sort of fall under that same big umbrella. The difference here from a precipitation reaction is we don't get a solid form, but we are forming water as a result of this reaction. Any questions on that there? Now, how do we get ourselves to sort of the water being formed here? And we could really write our same type of reactions that we talked about last time, which is if we look at this, we could break this molecular equation into our total ionic equation. So since HCl is a strong acid, it's a strong electrolyte, it will 100% break apart into H plus and Cl minus. Sodium hydroxide, also a strong base, which means it's a strong electrolyte. So it will also 100% break apart into a sodium ion and a hydroxide ion here. As we talked about before, when we get to like a total ionic equation like we're writing right now, there's really a few things we do not break apart. We don't break apart anything that's a solid. We don't break apart anything that's a liquid, and anything that's a gas or a weak electrolyte does not get broken apart. So our water here would stay together as it is a pure liquid, but our sodium chloride is a strong electrolyte, so it would break apart into sodium ion and a chloride ion. And this is our total ionic equation. And remember that when we look at our total ionic equation, we should be able to find our spectator ions. And in this case, the spectator ions are which ones? They are the sodium, as it looks exactly the same on both sides. And they are the chloride in this case. They are really the salt part, is really your spectator ions, is really where that comes from. Remember, the spectator ions essentially just get crossed out because they're there, but they're really not doing much to form the product. And what we're left with is our total ionic equation, our net ionic equation, which is basically the H plus from the acid, as I mentioned, and the OH minus from the base will come together to make water in our net ionic equation. So as I mentioned, doesn't matter what combination of strong acid, strong base you put together, if you go through the total ionic equation and to the net ionic equation, every single one will end up with the exact same net ionic equation for an acid-base reaction. When you're doing a strong acid, strong base reaction together, it will always end up H plus OH minus makes water. is always the net ionic equation that you end up with. Like I said, no matter what combination you do, you just have different spectator ions depending on sort of what combination you do, but it will always end up that same way. Any questions on that there? So again, this is another sort of class of double displacement reactions. And again, here, the formation of water is ultimately the goal of what's happening in this type of reaction. But again, if you can't remember that, just as this, remember the simple double displacement, flip around the ions. The key is to remember that when H plus and OH comes together, OH minus comes together, that obviously is water. So, you know, sometimes throws people off. That's why sometimes you'll see people write like HOH, which not technically the correct way to do it, but a lot of times people will write it like that, but that's really H2O. But if it helps you remember how to get there, you know, so that's sometimes how people sort of think of it. Any questions? Yeah. So this particular type of reaction is what is usually referred to more specifically as an acid-base neutralization reaction. And that's usually between a strong acid and a strong base, because ultimately what is being formed is water, which is why it's a neutralization reaction. It does fall under the big classification of double displacement reactions. So remember, there are really multiple ways you could classify the same reaction depending on sort of what you're looking at. There's kind of more specific ways to classify it, and there's sort of more of a broader sort of classification. And sort of the broader classification is double displacement. More specific would be acid-base neutralization reactions. Just like when we talked about the other day, precipitation reactions, that's kind of a more specific classification of the sort of broader classification of double displacement reactions. Other questions? Yes. They're still in the solution. So for example, we'll talk about kind of the two examples of these double displacement reactions, right? So you have all these positive and negative ions that are floating around, right? We'll just say before anybody finds each other in these type of reactions, right? Now, in a precipitation reaction, what happens is this positive and negative guy comes together and makes that solid, right? That is there. The other positive and negative guy is really the other spectator ions, and they're just floating around in the solution still. So they're just kind of floating around. In the case of what we were talking about in this one is same idea, really in this case, the H plus and the OH minus go and find each other. And they actually covalently sort of bond to make water, which again, we can't usually visually see we made water. But the other ions that would be there, like in this case, the sodium or the chloride ions, they're really just still floating around in the solution. Yeah. They're basically soluble is basically what's happening in this case. They're just, you know, floating around. They're not going to form anything or anything like that. Yeah. And most salts in most acid-base reactions, which is really where your spectator ions usually will come from, they usually will be some type of soluble salt, which means they're floating around. Basically, they're not going to come together to make any type of solid. There are rare occasions when they will, but in pretty much 99% of the time, that salt's just going to be soluble ions floating around in solution. But they're definitely still there. And that's why they're kind of like I said before, they're called spectator ions really because they're just watching, right? So, you know, there's guys watching the baseball game, right? In the audience, they're the spectators, right? And there's guys actually doing the work there on the field and playing and stuff like that. And that's sort of what's happening, you know, in this situation. They're there, but they're really not actively participating in any type of formation of a product. Yeah. Mm-hmm. Yeah.
Is there a time when you're going to use that water to do something else and then you have to remove sodium and chloride or whatever?
I would say in this example, for example, I think you actually made water the other day, and the last step, I think, where you did the indicator, I think. You started with some acid, I think, and you added some base to it, right? And you were basically making water. And that's basically what was happening there. But you kept adding base, and that's why the indicator eventually turned pink, because you added a lot of OH minus, way more than you needed, and the indicator picked it up. But to answer your question, I'm going to say yes and no. So water is involved in a lot of reactions that affect things like pH and acidity, and they're called hydrolysis reactions. So there are certain times when water and some other part of the salt actually will then start to react with each other. Not in this situation of a strong acid or strong base, but if you took like a weak acid and a strong base and put them together, you would still form water as sort of the overall result that's happening. But in that particular case, part of the salt part that you would form, those ions that are floating around, will then go, you know what, I want to kind of react with water, and it will actually continue to react with water. And in certain cases, what it will do is either make more H plus in the solution, make it more acidic, or it can make it more basic, which is actually what would happen in that case. It will make more OH minus and change base and make more OH minus in the solution. So although we don't think of water as maybe being really reactive, it's actually involved in a lot of reactions involving pH and acidity and basic type of solutions. So if you go to 1B, there's a whole section on salts and how they react with water and stuff like that. They're called hydrolysis reactions. But to truly answer it, there's really probably no situation where you'd go in there and try to remove the sodium ion or chloride ion. They're just in there all the time. You know? Yeah. Yeah. So for example, a lot of the solutions that we use in lab, right, are something nitrate, right, or something like that. And they use those guys as some version of the thing you're interested in with nitrate, because nitrate's soluble. So by doing that and using something that's like nitrate, right, it's soluble and everything, when you dump that solution in there, the nitrate is just going to hang out. It's not going to really react with anybody, but it's still in there. But it's really the other part of that, you know, whatever it may be, potassium nitrate, sodium nitrate, you know, silver nitrate, I think is maybe what we use. Like silver nitrate, for example, it's actually the silver part that's in there, but we could use a solution like silver nitrate because it's soluble in everything. So it could hang out in there and really not disturb anything. Yeah. Other questions? All right, so here's a couple other examples of some strong acid, strong base reactions. And again, if we took, you know, this one, you may look at it and go, well, you know, are we going to end up with water in this case? And we will. This is nitric acid, as we talked about earlier. It is a strong electrolyte or strong acid, so it would break apart into H plus and nitrate. Potassium is a strong base, has that hydroxide and group 1 guy in it, which means it will also break apart into potassium and hydroxide. Again, here we would keep water together as it's a pure liquid. This is a salt, which will break apart into K plus and our NO3 minus. So again, this is our salt over here. This is obviously our water that's being formed. And if we look at this, this is a positive, negative guy, positive, negative guy. So again, we know it's a double displacement reaction occurring here. And in this particular case, our spectator ions are nitrate, and it is our potassium. And those are our spectator ions. And again, you can see, even though it may look a little bit different, we do end up in our net ionic equation with H plus and OH minus coming together again to make basically water in this particular case. So as I mentioned before, typically our salts are usually soluble, but you know, there's a rare occasion where you could get the right combination where you might get a solid, but it's I would say very, very rare in most cases. You know, the salt will be very soluble. So that is sort of double displacement reactions. Any questions on any of those two main types of double displacement reactions? Okay. Yeah, so again, just to recap, our double displacement reactions, the big classification and underneath them is our precipitation reactions, where we form obviously a solid, and our acid-base reactions are the more specific ways of classifying those types of reactions. It's a precipitation reaction, yeah. Other questions? Yeah. It's not in this class, but yes. So later on, like if you take 1B, obviously, there's a whole section on acid-base chemistry, and you get into those combinations of what happens when you do like a weak acid, strong base, weak base, strong acid sort of combinations. So, and that's again where you'll come, as we talked about earlier, those sort of hydrolysis reactions and stuff like that. So, in our situation, I would say you might come across a question where it's a weak acid and a strong base, and or something like that. And again, the only difference would be if you had something like Let me see if I got a page or something. I can write it right here. So let's just say, you took a weak acid, right? And you had a strong base. Now, for our purposes here, it's still a double displacement reaction. So hydrochloric acid is a weak acid. Sodium hydroxide is a strong base. And again, if you just look at it, positive, negative guy. So these guys are going to switch partners. So these can go over here, and this is going to go over here. And the result of this is, again, our H plus and OH minus, or H plus from our acid, or OH minus from our base, is still going to make our water. And our salt's actually going to be the sodium ion and the fluoride ion coming together, which would make NaF in this particular case. And this would be our molecular equation. The difference would be is if you understand something is a weak acid or even a weak base is, again, it is a weak electrolyte, which means it will mainly stay together. So where the difference comes in would be in the total ionic equation. When we would go to the total ionic equation, because this guy is a weak acid, we would actually keep it together. Again, because it's a weak acid, it's a weak electrolyte, it's mainly going to stay together in solution. We would still break apart the strong base in this case, which would be our sodium ion and our hydroxide ion. Our water would still stay together. And our sodium fluoride, which is a salt, will also break apart. So the main difference that you'll see if you in our sort of part of the class here is if you come across something that's a weak acid or weak base, you would want to keep it together in the total ionic equation. And what that's going to affect is, in this case, which ones are spectator ions in this case? It's actually the sodium. And is there another spectator ion here? There actually is not. So there's nothing on either side that looks the same other than sodium. So you'll actually end up with only actually one spectator ion here. And what you would have is still the HF together for the net ionic equation, plus the hydroxide from the strong base, making our water. And you would have that F minus that's floating around. And this is what the net ionic equation would look like. Again, because we had that weak acid involved, and our weak base would work out the same way. And that would actually be what you have floating around the solution. And then tie it together what we were talking about a second ago. It is actually this F minus in this real life situation here would then decide, I want to go and continue to react with the water that's there. And that's what I was talking about earlier. It would continue to react, actually make more hydroxide in that solution. And it actually would be, a little bit more basic at that point because of that. Any questions on that? So for our purposes, if you do come across a weak electrolyte, a weak acid or weak base, the only difference would be in that total ionic equation. You would want to keep it together and not break it apart. And you would learn further about it, obviously, if you continue on to 1B. Other questions? Electrolyte is something that when it breaks apart in solution produces ions and it's able to conduct electricity. Other questions? All right, then let us talk about the next big classification of reactions, which is redox reactions. These are oxidation reduction reactions. They again are sometimes called just straight up redox reactions for oxidation reduction type reactions is what it means. These things always occur together. So that's a really good thing to keep in mind. If you can identify something as being oxidized or going through oxidation, that means there must be somebody there that is going through reduction. This is the third reason why a reaction takes place. These all involve ultimately electrons being transferred. So this all involves really electrons being transferred in these type of reactions. So when we talk about oxidation or reduction, there are some definitions. When we talk about something that is being oxidation or oxidized, it typically means that it is losing electrons. When we talk about something that is reduction or going through reduction, it is something that gains electrons. Later on, there's a couple other definitions of oxidation and reduction that involves hydrogen and oxygen. If you take organic chemistry, you'll learn a lot about, their definitions, so we won't get too much into it here. Sometimes people remember this by Leo the Lion Goes Grr, Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. So how can we determine if something is being oxidized or something is being reduced? There is really sort of a simple way that you could do it. You could literally just make a number line. It's usually 0 in the middle. To the right are positive numbers, to the left are negative numbers. When somebody loses electrons, do they become more negative or more positive? They do become more positive, right? They got more protons than electrons. So if you see the charge or what is really called oxidation number or oxidation state of something become more positive or moving in this direction, that thing is being oxidized or going through oxidation. When somebody gains electrons, because they gained electrons, they become more negative. So if you see somebody moving in this direction on the number line, they are going through reduction. And that's sort of a simple way to figure out what is going on just by whichever way you're going. We can oftentimes do that by looking at the charges, or what is again sometimes referred to more correctly as the oxidation states that are going on. Now, there's also something known as the oxidizing agent and the reducing agent. Now, when you're talking about the agent, not what is being oxidized or what is being reduced, but the oxidizing agent or the reducing agent, the easy way to remember it is it's opposite of the name. So the oxidizing agent is the substance that gets reduced. While the reducing agent is the substance that gets oxidized. So why are they called that? Well, they are called that because let's talk the oxidizing agent first. In order for something to be oxidized, it has to lose electrons. And in order to make something lose electrons, somebody has to gain those electrons and be reduced. So the guy that is being reduced needs to gain electrons from somebody. That's going to cause the oxidation in somebody else because they lost electrons. The reducing agent is the opposite. When that guy gets oxidized, he's going to lose his electrons, which is going to cause somebody to pick up the electrons and become reduced. So they're called agents because they cause the opposite effect in the other guy. Any questions on that? So we'll take a look at one here to kind of see we can identify those things. By the way, when we talk about redox reactions, like I said before, that is much like double displacement. That's really the broad classification of a type of reaction that's occurring. And ultimately, it's electrons being transferred that are occurring here, which is that third driving force. So if we look at this reaction here between sodium and chlorine, what is really happening here? In this particular case, the sodium is by itself. So if you think about when we talk about things being by themselves, they do not have a charge, right? Things only get a charge when they kind of hook up, a metal and a non-metal come together. So ultimately, this guy has a 0 charge or really oxidation state. Chlorine, which is Cl2, that is naturally the way it comes, right? It's one of those diatomic molecules. It also is not hooked up with anybody else and really has no charge or no oxidation state. When the sodium, the chloride come together, that is really when they do gain charges, right? So here on the right-hand side, the sodium has a +1 charge. The chloride has a -1 charge. So if we think about what is happening, like I said before, you could just do a simple number line here. And if we look at the sodium, for example, sodium is starting at 0, which would be like here. And it is ending on the right-hand side at +1, which means it is moving in this direction, which means it is becoming more positive, which means the sodium is being oxidized or reduced. Oxidized, good answer. No. So yeah, so when you become more positive, right, you're being oxidized or going through oxidation, and that's because you're losing electrons, so you're becoming more positive. By the way, once you identify sodium here as being oxidized, the chlorine is going to be reduced. They always happen together. So you don't even have to identify them both. You can figure out one. That's all you need in these type of reactions. But we could even look at the chlorine in the same situation. Chlorine is starting at 0. And where's chlorine ending up on the other side? It's ending up at -1, which means it's moving more in the negative direction and is going through reduction in this case and being reduced. So in this particular case, the sodium is being oxidized. The chlorine here is being reduced. And ultimately what is happening here is that electron whirly miss is the electron is being transferred from the sodium to the chlorine in this particular case. And in this case, because the sodium is being oxidized, that makes the sodium the oxidizing agent or reducing agent. It is the reducing agent, is the opposite of what's happening to it. And the chlorine here, which is being reduced, would actually be the oxidizing agent. So when we take something like sodium and put it together with chlorine, we make sodium chloride. It's basically how all ionic compounds are formed, right? We talked about when we did bonding and other things. It's basically electrons being transferred. So all formations of ionic compounds are really these redox reactions that are taking place. This could be classified as a redox reaction because that is ultimately what is happening here. Any questions on that there? Now, if we look at this, though, there is really another classification that we can look at, which is this is also what is referred to as a synthesis reaction. Our combination reaction, which I think we'll see in just a second. And that is when two things come together to make one thing. So a more specific classification that you could do for something like the sodium and the chlorine coming together is call it a synthesis or combination reaction, but ultimately it is a double displacement reaction. If we look at magnesium and oxygen, which you also did, first one with the crucible tongs, where you observed it but did not observe it, right? As you got blinded that day, right? So that is actually this reaction right here, by the way. That way, hopefully that's what you wrote for that one, I hope. But this is magnesium, which is the magnesium strip by itself. Uncombined, it has no charge. The oxygen in the air, naturally the way it comes, uncombined has really no charge or oxidation state. When they came together, which by the way was the white ashy type stuff that ended up on the crucible tongs or maybe on the countertop there at the end when it kind of got very bright, that is the magnesium oxide coming together. And in this case, the magnesium has a +2 charge, the oxygen has a -2 charge. And again, if you were trying to figure out what is being oxidized and what is being reduced, the magnesium is starting at 0 and ending at +2. So the magnesium is being oxidized in this case. The oxygen is actually starting at 0 and ending at -2, which means it's going to the left here and becoming more negative, and it is being reduced in this case, which would be the oxygen. That means our oxidizing agent in this case is actually the oxygen, and our reducing agent is the magnesium in this case. So this also is a redox reaction that is really taking place here. Electrons are being transferred from the metal to the non-metal. By the way, like we talked about with naming and bonding, whenever a metal and non-metal come together, you always get the electrons being transferred. It's always a redox reaction. And it is always the metal that will lose the electrons like we talked about and be oxidized. And it's always the non-metal in that situation that will pick up the electrons and being reduced. So you can even simplify it even quicker for yourself if you're ever asked what is being oxidized and reduced, and you have a metal and non-metal together. Metal always going to be oxidized, non-metal always going to be reduced. And again, that's a case obviously specifically for metal and non-metal when they come together, which is really an ionic compound. This also could be a synthesis or combination reaction. basically two things make one thing. So that's your classic combination or synthesis reaction. And again, looking back on the previous page there, two things making one thing is your classic combination or synthesis reaction, which again is a more specific classification of this type of reaction. These are what are sometimes referred to as the half reactions in this reaction. And this is the oxidation half reaction. This is the reduction half reaction that's happening here. They're called half reactions because they're half of what is going on. And half of the case, the guy is losing electrons, and the other half of the case, the guy is gaining electrons. If you ever are given anything that's like half reactions in a redox situation, the way you could quickly recognize is that a oxidation half reaction or a reduction half reaction is what side you see the electrons on. If the electrons are on the product side in a half reaction, that means they are being given off or lost, and that always signifies an oxidation half reaction. If you see the electrons on the reactant side, that means that those electrons are being gained, like what happens when something goes through reduction. So that is always a signal that that is a reduction reaction. So product side for your electrons, oxidation. Reactant side for your electrons, reduction half reaction. They're called again half reactions because basically when you put them together, you get the overall reaction that's taking place, which is the bottom reaction there, the magnesium plus the oxygen, making the magnesium oxide. And by the way, the electrons are always the same in both half reactions, the number of electrons, because in a redox reaction, however many electrons somebody loses is how many electrons somebody gains. So it's like a perfect sort of transfer of electrons from one thing to the next. So the magnesium ultimately gave up 4 electrons, 2 from each of them, right? Because magnesium is +2, right? If you have 2 of them, that's +2 + 2. This is 4 electrons. And oxygen here, which is 2 oxygens, which each make a -2, right? Which means they each pick up 2 electrons for 4 electrons total in this type. But the electrons should always cancel out. They always should be the same amount on opposite sides of the arrow when you're dealing with half reactions, because it should be sort of a perfect transfer of electrons from one place to the next, basically. Any questions on that? Yeah. Say it again. It's not sharing electrons. Synthesis or combination is a kind of like what we were talking about earlier with double displacement, and then you could specifically call it like a precipitation reaction or a acid-base reaction. The big umbrella is redox reactions, and a more specific classification of this particular type of redox reaction is a synthesis or combination reaction, which is 2 things basically make one thing. So if you just simply look at this reaction, the overall reaction on top, you basically have 2 things on the left, makes like one thing on the right, which is why it's sometimes called a combination reaction, like put them together, combining them together to make one thing. Yeah. Other questions? Synthesis or combination. So a lot of people will call it synthesis, a lot of people will call it combination. So they're interchangeable sort of labels for this more specific way of classifying. Yeah. All right, we're not going to get into that. I think we'll skip that there. All right, so as we talked about, we've now seen sort of the 3 places and reasons why reactions take place. Again, these first 2 are in the big umbrella of double displacement, and we're currently talking right now in the big umbrella of redox reactions with our transfer of electrons that are happening in this particular case. So earlier, we sort of got into this, but again, a precipitation reaction is a double displacement reaction. And again, as we saw and we talked about earlier, take 2 things, and it is that solid that is being formed that makes it a precipitation reaction. And a reminder, though, that it is still a double displacement reaction. Our positive, negative, potassium goes, finds the nitrate, barium goes, finds the chromate. And again, one of these combinations here making that solid. So big classification of this type of reaction, and the one like we made the other day, the yellow everywhere, that's hopefully still in your drawer, is again double displacement, more specifically a precipitation reaction occurring. Yeah. The third one's a redox reaction, yeah. Is the big classification of it. Yep, okay. So again, double displacement is our precipitation reaction and our acid-base reaction. And ultimately, it's always the same combination, the way you recognize it, positive, and negative. And again, there's no other type of reaction that starts that way, always that combination. We talked about that switching place is pretty good. And then obviously our acid-base reactions, again, that more specific way of classifying our double displacement, positive, negative, again, that formation of water here. So let's get into some of the more specific ways to classify redox reactions. And here's a couple here. Let's take a look at these. There we go. Okay, so these again are more specific ways to classify redox reactions. This first one, as I mentioned before, is our redox reaction. Again, if we look at it, 0 for the lithium because it's by itself, 0 for the fluorine because it's by itself, +1 and -1 here. And again, if you just did the number line, we once again see our metal starting at 0, becoming more positive, so becoming oxidized. Our fluorine starting at 0, becoming more negative here. So it is becoming reduced. I think I misspoke, becoming more positive on the oxidation in this particular case. And again, even without all that, lithium is a metal, fluorine is a non-metal, so I should know my lithium is going to lose the electrons and become oxidized, and my fluorine is a non-metal, should gain those electrons and become reduced without even thinking or figuring out the charge in this particular case. Another type of redox reaction is a single replacement reaction. And the way you recognize these are one of two ways. We have A plus B, C. So in this particular case, this guy here will be perhaps a metal that has no charge by itself, not combined with anything else. And then you will have some type of ionic compound with it. So that's different than double displacement where you have two ionic compounds. In this case, you have something by itself uncombined with an ionic compound. If it is a metal, as we know, it will become positively charged, which means it will come in and kick out the positive guy. And the result of that is you will make a new ionic compound. The guy coming in will then gain a charge, a positive charge. The negative guy will combine with it. And actually, the guy that started out here with the positive charge will come out and actually have no charge. And that's exactly what is happening in this reaction right here. That is zinc, which is a metal by itself, has no charge. This is hydrochloric acid, which is really an ionic compound, which is a positive negative guy. In this reaction, it is the zinc that comes over and kicks out the hydrogen in this case. The result of that is hydrogen comes out by itself, which now has no charge. By the way, this would be like in your test tube where you start to see bubbles form, right? Like when you did the magnesium, the hydrochloric acid, exact same reaction, basically. Those bubbles that you see is the hydrogen gas that's happening. Now the zinc, which originally had no charge, will gain a charge of +2 when it combines with chloride, which is -1 in this particular case. And that is a classic single replacement reaction. Whatever is coming in order for the reaction to take place, needs to be more reactive than what it is replacing. If it is less reactive than what it is replacing, the reaction will not take place. So if you substitute out, I can't say the right symbol there, copper there, I was going to say carbon, but copper would be a better shade. You took the copper with the hydrochloric acid. Copper is actually less reactive than hydrogen, and it will not replace it. and the reaction will not take place. So you won't really see anything occur. But if you substitute out zinc for it, it will definitely happen. Magnesium, for example, will happen as well. So there are some other ones. Now, we also saw this type of reaction. If I think I mentioned in the lab as well, when we did those halogen ones, as we talked about, I think the other day as well. In this case, the A could actually be a non-metal. And you can have B, C, which is our positive, negative guy. And if A was a non-metal, which has no charge to begin with, it will actually go in and kick out the negative guy, right? Because non-metals become negatively charged. And when it does so, it will make a new ionic compound. The guy coming in will then gain a charge. The guy going out will not have a charge. So if you remember, we did the halogens, right? Reactivity increases as you go up group 7, right? We saw the colors change in the top layer versus the bottom layer in that experiment a while back. And, you know, so if we had something like Cl2 plus NaBr, this is something by itself, has no oxidation state. That is a positive, that is a negative. This guy is then going to go in and kick out the bromine here. It's going to make a new ionic compound, which is NaCl. And then the bromine will come out by itself with no charge. Again, positive and negative guy here. Probably should do a little balancing to be all correct. There we go. But this also is a single replacement reaction. It's just like that experiment we did early on when we talked about reactivity of group 7. And it's also occurring here. So a more specific classification of this type of reaction is a single replacement reaction. A more broader classification of this is still a redox reaction, because if we just take a look at this original reaction here and we do our number line, the zinc is starting at 0, ending at +2, moving in the right direction there. And that means that the zinc in this case is being oxidized. It is actually, in this case, the chlorine. When we look, I'm sorry, it's not the chlorine. It is actually the hydrogen in this case. The hydrogen is starting at +1, which would be like right here. And it is ending at 0 on the right-hand side and is going in this direction to the left there, becoming more negative. And it's actually the hydrogen part here that is being reduced. So it is still a redox reaction that is happening here. Still electrons being transferred, but probably 9 times out of 10, if somebody asked you to classify this reaction, they would call it a single replacement reaction rather maybe than a redox reaction, but it is still a redox reaction. Now you may be asking yourself, or maybe you're not asking yourself this, but you know, what is happening with the chlorine? The chlorine in this case is really just it's probably the second I know. The chlorine is really a spectator ion in this case. You could actually write a net ionic equation. I'll go back. If you took the zinc, which is a solid, plus our hydrochloric acid, making our zinc chloride here, plus our H2 that's coming out, which is a gas. And in this case, we need a 2 there, I think. You could write a total ionic equation. We follow our same rules. So since zinc here is a solid, it obviously would stay together, no charge. That is a strong acid, which means it would break apart into H plus and a couple of chlorides as that 2 gets distributed to everybody that is here. On this side, the zinc would break apart into zinc plus 2 and a couple of chlorides. And our hydrogen gas would stay together. In this particular case, it is the chloride here that is the spectator ion, which gets canceled out. And the net ionic equation that is happening here is actually this, which is the redox part of it. It is the zinc going from no charge to +2. It is the hydrogen going from +1 to 0. And that is the net ionic equation of ultimately what's happening here. So also to an earlier question, again, the chloride is just kind of floating around still in the solution, not really participating or doing any part of the electron transfer part of it. The zinc is being oxidized here. Again, if you follow the number line starting at 0 and becoming +2, again, it is becoming more positive, which means it's losing electrons and becoming oxidized, is the hydrogen that's starting at +1 and actually moving towards 0 in this case, which means it's actually becoming more negative, even though it did become negative, but it's moving in that negative direction. And the only way it could do that is to actually gain electrons in this particular case. So the hydrogen here is being reduced, which would mean the hydrogen is the oxidizing agent. And the zinc here, which is being oxidized, would be the reducing agent. Yeah, in this case, yeah. Other questions on that? Okay. So again, a more specific classification of redox reactions is this type of reaction where you have something uncombined plus an ionic compound, single replacement reaction. Another classification of redox reactions is really combustion reactions. And there's two types of combustion reactions. There is these types right here, which is basically what most people consider combustion reactions, which is some type of organic guy, which is these guys. An organic guy is something like carbon, hydrogen, and oxygen. And the way you could definitely 100% know it's a combustion reaction is if you look at the equation, you see O2 on the left-hand side and you see CO2 and water being produced. Just write combustion. It's always that guy for sure, especially obviously the guy on the left there is carbon, hydrogen, oxygens. It's 100% combustion. You did, maybe some of you did it, some of you didn't when you burnt the countertop the other day. Yeah, that was a combustion reaction, right? When you light your Bunsen burner and you put it on there. You probably saw, or if you did it or didn't do it, when we tell you what you should have saw basically some condensation occur. Yeah. And that is because water is being produced here. And the benchtop is super cold most of the time, right? So that water being produced hits the cold benchtop really quick. You see like kind of condensation occur for a second, and that's really what you were seeing in that particular one. And again, that's the most of the time what people would consider a combustion reaction. There is actually a very, very basic definition of combustion reaction, which is simply you got O2 involved. So if your basic definition actually of a combustion reaction is you simply have O2 on the left-hand side. And that's why the other reaction we just saw where we actually did as well, this one where we formed magnesium oxide here. This, as we talked about, is a redox reaction. You can classify it. This is also a synthesis or combination reaction, right? Two things making one. You could even thirdly classify this, technically speaking, as a combustion reaction because there's O2 involved. So as you can see, there are sometimes multiple ways, the exact same reaction, you could classify it. You want to kind of pick the right classification based on maybe what you're looking at or trying to identify. But yeah, that particular reaction right there, 3 different ways you could classify it. Redox, most people again would probably classify as synthesis or combination, but it could also fall under this sort of umbrella of combustion reaction because O2 is involved. Any questions on that there? But I would say probably 9 times out of 10, combustion, most people think about what we see on the screen there on the left, O2 on the left, CO2 and water, and this sort of organic combustion reaction is usually what people kind of think about. So there's our synthesis and combination. The formation of water. And again, this is just basically 2 things making one thing. And that's classically what we see here. Hydrogen gas, oxygen gas, 2 things make one thing, synthesis or combination. The sodium and the chlorine, 2 things make one thing, again, synthesis or combination. Each of these also, again, a redox reaction is ultimately what's happening in each of these cases. The last type of classification, I think, is really the opposite of that. That should be synthesis. I'm not sure why it should be synthesis. The last type of reaction that also falls under sort of the redox umbrella is the opposite of this reaction, which is a decomposition reaction, where we basically take one thing and break it apart into 2 or more things. So it's really the reverse of this reaction, which is we're just going to take one thing and basically break it apart, which we also did. If you take A, B, making 2 or more things. You did that with the 9-volt battery, right? The little guys with the electrodes, and you saw the bubbling occur, right? And if you run an electrical current over water, one thing breaks apart into two things. Along the way, I think we did like an Alka-Seltzer tablet or something like that. But anything that has sort of that forms something like carbonic acid will break apart into water and CO2, for example. I think we did it somewhere along the way in one of those reactions. But basically, one thing makes two or more things is your classic decomposition reaction. So synthesis combination, you put it together. Decomposition, basically the exact opposite of it, one thing and you break it apart. Single replacement, somebody comes in and kicks out somebody. And obviously double displacement, we have the exchange. Any questions on classifications? So just to summarize where we're at here in terms of these guys, which is the end of this chapter is really where we're at. But we have our double displacement, which is again our big umbrella of reactions. And underneath those, as we talked about, is more specific ways, which is a precipitation or an acid-base reaction. Got an extra T in there, precipitation. Our redox is our other big umbrella for which we have more specific ways of classifying synthesis or combination, decomposition, single replacement, and combustion reactions. So again, the top one, big umbrella, big classification of reactions. Underneath a more specific way you could classify those type of reactions. Any questions on any of those classifications there? Okay, that should wrap up chapter 7 here.